Hello, Nikodem.
Hello,
Hello. It's early morning in Boston, I guess.
I'm in Milford, Connecticut.
You're in Connecticut, of course. Yes.
Connecticut is the neighbor of Massachusetts.
Yes, and right above New York.
And I think exactly it is somewhere between New York and Boston.
Okay, okay. And here it's afternoon, and we are very delighted that you want to talk to us. You come from Europe yourself, right?
I am originally from Poland. I was born in the city of Toruń, which is the birthplace of Nicolaus Copernicus. So I always tell my students that I'm somewhat connected to astronomy.
That's quite an impressive people to have come from your town. And so, what we want to talk to you about today is that you've been gotten a lot of notice because you maybe first explain to us what you do on the university, what you study, what you teach, and yeah, how that became that famous theory of yours.
So I have been teaching at University of New Haven in Connecticut for the last 12 years, and I teach introductory and advanced physics. Some of my classes include general theory of relativity or advanced mechanics. General theory of relativity, Einstein's theory, is my favorite physics, one of the two pillars in physics, in addition to quantum field theory. And as a researcher, I try to answer some fundamental questions about the universe. I'm deeply curious about how the universe originated, what is the nature of black holes and matter, antimatter asymmetry, dark matter, dark energy. They are like fundamental questions that it seems like that we don't understand completely everything. We made a very great progress and observational theoretical, but there are some questions which need to be answered, and this is my goal.
Yeah. So
So a research detective of mysteries.
Mysteries, yes.
yes, that's what we love in this program as well. um, so let's dive into it. Because can you explain to our listeners the theory that you have about our universe and about black holes and how those two things are related?
I believe that every black hole creates a new universe on the other side of its event horizon. The event horizon is a boundary of a black hole through which matter can go in but cannot come out. The motion of matter through an event horizon is one directional. And if this theory is true, then our universe was born in a black hole, existed in some parent universe. This theory is based on the oldest extension of Einstein's theory of relativity, which is called Einstein-Cartan theory of gravity, which was proposed in 1921. So this is 5 years older than the famous Schrödinger equation of quantum mechanics. Einstein, creating his theory, discovered that space-time is curved by matter, and at the same time, space-time tells matter how to move. So there is like the constant interaction between space and time and matter. Einstein introduced the curvature of space-time to the equations, which was based on mathematics done by Riemann and Ricci, like earlier. And he assumed, for simplicity, that torsion, which is another a property of space-time in addition to curvature, he assumed that torsion is equal to 0. And Cartan generalized Einstein's theory, and he basically postulated that torsion does not have to be 0. It can be whatever value it wants to be, and the equations and the presence of matter will decide what torsion is. But the biggest progress in Einstein-Cartan theory came like in the 1960s, when two physicists, Sciama and Kibble, and Sciama was doctoral advisor of Stephen Hawking, and Kibble was one of the 6 physicists who co-discovered the Higgs mechanism for originating the mass of weak bosons. Sciama and Kibble discovered in the 1960s that torsion can be produced naturally by spin, which is the intrinsic angular momentum of matter, which is like one of the fundamentals of quantum mechanics. But the interesting thing was discovered in 1970s by physicists such as Hell or Trautmann. They discovered that spin and torsion together, they manifest themselves as gravitational repulsion. So normally gravity is attractive force, but at extremely high densities, much higher than nuclear density or density in neutron stars. Neutron stars have density 10 to the power 17 kilograms per meter cube, like water is like 1000 only, but at densities approximately 10 to the power of 40, so much higher than nuclear stars, torsion becomes significant, and it opposes curvature. It acts like gravitational repulsion. So where matter would like to collapse to a singularity, which is the prediction of Einstein's relativity, if nothing can stop matter from indefinite collapse, then matter will end up at a singularity, which is defined as a point or maybe set of points where density of matter and curvature of spacetime are infinite, which means physics breaks down. It was discovered that thanks to torsion, a singularity can be avoided, which means, and we have two kinds of gravitational singularities in standard Einstein theory. One is a final singularity in a black hole where matter collapses to a point, or a ring for rotating black holes. And we have also the Big Bang singularity, which is the beginning of the universe. So it was discovered that torsion can avoid those singularities, which means that the matter in a black hole does not collapse to a point, but it will stop at some extremely high density. But then after that, it has to expand again, because the space-time inside a black hole is non-stationary. It cannot be at rest. So the matter cannot just stop. It has to expand back. And also at the beginning of the universe, the Big Bang was not a singularity. It was the finite density state, very hot. However, this suggests that there was something before the Big Bang, because we can analytically continue the space-time backwards in time. So we can, there was the past to the Big Bang. And
so
and
something
also
before the Big Bang. is
Yes, before the Big Bang, that there was something. And also, if there is no singularity at the final stage of the matter in a black hole, then the matter, instead of singularity, it wants to expand back, but the matter cannot go back through the event horizon of the black hole because the motion is only in one direction. So, and yet the matter has to be moving, so there is no other choice. The matter must create a new space into which it will be expanding. And mathematically, this is equivalent to a new closed expanding universe, which happens inside the black hole, or maybe I should call on the other side of the event horizon, because the other side of the black hole, the other side of the event horizon is much bigger than the black hole itself. So it's from the outside, it looks like inside, but from the outside, for the outside observers, they think that a black hole has the interior, but really this interior is much bigger than the black hole itself. It's like a door. Instead of being a door to a closet, which is as big as the door, it is analogous to a spherical door to another space outside, basically. So, so because of this avoidance of singularity, there is something after the matter reaches this final super dense state, and there is also something before the Big Bang. So it is natural to combine those two things, and the final singularity in a black hole becomes initial singularity of a new universe at the Big Bang of that new universe. And this is the idea which Lee Smolin suggested. However, he suggested that with the singularities, and what I proposed was that because of the torsion, there is no singularity, and this transition from the final stage of the matter collapsing in a black hole and the beginning state of a new universe in the black hole, they are combined smoothly without any singularities, any infinities. Everything becomes a regular transition, which means the laws of physics and the constants of physics can remain the same. Smolin suggested they might be changing because of the singularity, but if nothing is singular, if everything is finite, then this transition can happen naturally. So basically, my contribution, I would say, was that because of the torsion, every black hole can create a new universe, and this is because of that gravitational repulsion of torsion, which is almost zero at normal densities. We don't need torsion on Earth or even in neutron stars, solar system, in the galaxies. Torsion is almost zero. Miraculously, removing the constraint that torsion is equal to zero, which was done by Einstein. Einstein assumed that torsion is zero, but the field equations allow torsion to be not zero, and it is almost zero anyway. So there is no need to assume it is zero, because the equations will say that at our densities it will be almost zero anyway. So we don't need that. But at extremely high densities, torsion starts being much bigger than zero, and this is where we need that, because we have to fix the theory. So in my opinion, torsion is the mechanism which allows for elimination of singularities, make all physics finite, and as a result, black holes make new universes.
So it's more like, one should think of, instead of Big Bang, like out of nothing comes everything, which is basically sort of the usual theory. It's more like a phase transition where it was there, but then it established itself as a new phase when you have to talk and it starts expanding.
Yes. Like the phase transition, the torsion becomes significant, matter becomes gravitationally repelled, and there's a transition from the from the matter inside the black hole creates a new universe, yes. And
can I ask a possibly super naive, maybe even stupid question? So is every black hole a universe, or is it like you want to think of it as every black hole has the potential of forming a universe? Because I'm thinking you constantly have matter falling into the black hole. So I was just wondering, would we, if we are a black hole, also expect to see matter entering our universe from wherever the phase transition started? Because
this is a great,
I'll be
great
very
question.
happy about that, because then there would be an observable parameter, right? Then you would actually be
Yeah,
able
of
to think
course.
about how you could go out and test
Yes. So if if our universe was formed like within the event horizon in the interior of some parent black hole existing in some parent universe, then from our perspective, so there's an entrance from the parent universe to the baby universe, which is our universe. So we are in the baby universe. So we could potentially, theoretically, still see the Einstein-Rosen bridge, which is the connection from the parent universe to the baby universe. It is a mathematical solution of Einstein's equations as well, but without torsion, that solution would never be mathematically realized. So in Einstein's theory of relativity, a black hole, which is the mathematical solution of gravitational fields with spherical symmetry, there are three solutions: black hole, white hole, and Einstein-Rosen bridge, which is a wormhole, which was the solution discovered by Weil, but he dismissed that as a very strange solution. Einstein relativity theory allows only one of those solutions, a black hole, to be naturally formed, because white hole would be very strange. White hole is like a time reversal of a black hole, that matter, instead of going in, it comes out. But the question is, where would it come from? So, however, if every black hole, thanks to torsion, becomes actually is a wormhole, Einstein-Rosen bridge, which is the mathematical solution of Einstein's equations, even without torsion. But torsion is a mechanism which allows that solution to be chosen instead of a black hole. So we have Einstein-Rosen bridge. So if we are inside a black hole and in this new universe, then if we look at that bridge, then from the other side, it looks like a white hole. So there would be, of course, the matter coming in. But realistically, that black hole, this parent black hole, is probably right now lonely. So like it ate all the matter around. So if there was some matter coming from the parent universe to our universe, it probably happened long time ago. And right now, nothing is going in. So if we ever find that white hole, because if this theory is correct, then in our universe we will observe one and only one white hole. We will not know where it is, but this white hole will look like some object. It will look like a black hole, except that matter could be coming out, but it will not, probably, because it happened a long time ago. So
and that would be entrance to our universe.
Yes, this would be
Yes.
the entrance from the parent universe to our universe,
Yeah.
that white hole.
Yeah. So in this theory, we would be able to go to other universes.
We would, I mean, we could do it, except that now this is an interesting thing, that this theory assumes the existence of a multiverse, that there's more than one universe. However, right now, for us, our universe is the only universe, because there is something called gravitational dilation of time. Time is slowed down by gravitational field, and time is relative, which means time on Earth runs at a different rate than time near an event horizon, near the event horizon of a black hole. So at the event horizon, the time measured by observers there is slowed down relative to time on Earth. And actually, at the event horizon, the ratio becomes 0, which means time at the event horizon is frozen relative to our time. This does not mean that the observers going to a black hole will see something strange. Actually, a person on a spaceship going into a black hole will not notice any change in their time. The time on the watches will be running normally. They will be aging normally, like for themselves. However, from the perspective on the time on Earth, their time will be slowed down, so they will be aging more slowly than the people on Earth. So if they meet again, they will see the difference that people near the black hole are a little younger, or maybe much more younger. So time at the event horizon of a black hole is frozen relative to our time. That means that we will never see the observers on Earth. We will never see anything coming into a black hole, because the time for the observers on Earth, the time necessary to reach an event horizon for any object falling into a black hole is infinite, which means everything will fall into a black hole after infinite time as measured by Earth. But this means we can also extend this analysis. Let's say that we have a star or the center of galaxy, which is forming a black hole, and we put an observer on the surface of this sphere, which is collapsing to a black hole. For the same reason, a sphere collapsing to a black hole will reach the event horizon. It will after infinite time as measured on Earth, because it will be in the gravitational field, the Schwarzschild metric. So the event horizon forms after infinite time as measured on Earth, which means for the observers on Earth, black holes don't exist. All black holes we see at the centers of galaxies or other like intermediate black holes or stellar black holes, supermassive black holes, all the black holes we observe are almost black holes. For us, they are almost there, but they will never be a black holes. Now we know that they are black holes because the measurements of the radius and mass of those black hole candidates tell us that they will be a black holes. In their own time, they are probably already they are already black holes. But for us, we will never observe it, which means from our perspective, all black holes form after infinite time, and this is the relativity of time, which means everything which is happening after also happens after infinite time, which means from our perspective on Earth, all the new universes are not born yet. They will be born after infinite time. However, if we want to choose one black hole and go inside and see what happens, then we will discover that on the other side of the event horizon, there is already a new universe, and so we will say, oh, there's another universe, but then we cannot go back. We cannot tell anyone what we found. So this universe will be now our one and only one universe. We can forget about the parent universe because we cannot go back. We may hope that maybe some friends come after us and we can tell them, but they will see it themselves that there is a new universe.
Wow. So it comes with a price.
It comes with a price, and basically this new universe will be our only universe this will be our new universe, the only one.
But
And
in theory, you would be able to jump from one universe to the next and then into a new one and into a new one, right?
in theory, yes, of course. If you go to a new universe and that universe has to be already big enough, because we may come to a universe which is still like young and hot, and it would be a disaster to live there.
Yeah.
And there may be no new black holes. So
Would
so
we
it would be
expect the physics to be the same then? Because that's what I hear you say, right? So we expect the physics to be the same.
yes.
The age might not be the same, but the physics would be the same. So if
So I
you're
believe, yes, the age.
lucky, then it could be similar to ours, but it could be younger or older, or
It could be similar. Like, I'm still working on a calculation how to check, because it would be, let's say, if some people would like to go to a black hole, it would be great if they know beforehand whether the universe on the other side is already good to go, or maybe it's not good to go yet. But I don't know yet the answer. But yes, I believe that the new universe on the other side of the event horizon of a black hole would have the same laws of physics, because the big bounce, which is replacing the Big Bang, the big bounce is a non-singular regular event. Space-time is continuous because torsion prevents an infinities from happening. If there is no infinities, there is no discontinuities, everything is continuous. So if space-time is continuous, there is no reason for any like abrupt change of laws of physics or dimensions or constants of physics. So I believe that this new universe will have still 4 dimensions like space and time as we have, and the speed of light, gravitational constant, Planck constant, electric charge of electron, they will be all the same in the new universe.
Could we fly what would happen if we flew a drone or something with a camera or audio equipment? Would there be any way to keep something connected to our universe from this new universe?
Unfortunately, no, because a black hole is defined as the region of space-time from which nothing, even light, can escape. So no, light cannot come out, and nothing is faster than light. Now, of course, quantum mechanics is still like not completely understood, because we have phenomena such as entanglement, which means that like 2 particles can appear to communicate with each other much faster than speed of light, and the experiments proved it like many times. And there is some hypothesis that maybe on quantum level, on subatomic level, matter can actually communicate with each other with superluminal signals faster than speed of light. But then when we go to classical limit of quantum mechanics, then everything is suppressed and we cannot use it for our life, like to communicate faster than speed of light. But maybe on quantum level, moving faster than speed of light would be possible, and maybe this would allow some signals to come out of a black hole. But the problem is that so Einstein relativity theory does not exclude motion faster than speed of light. However, some objects are invariants, which means they are the same for all frames of reference. So basically, if a particle moves slower, if something is moving slower than speed of light, it will be always moving slower than speed of light in all frames of reference. If light is moving with speed of light, it always is moving with speed of light in all frames. Same thing would be with those objects moving faster than speed of light. If they move with speed of light, they will be always moving with speed of light in other frames of reference, which means in order for those objects to maybe come out from the black hole, they would have to be created first, moving faster than speed of light on Earth, but we cannot. I don't think there's an evidence for any things we can create which could move with faster than speed of light. So I don't think it's possible to make those objects and then put them into the black hole and hope that they will come out. But this is just my guess. Like, I'm not expert on superluminal relativity. There is some research, actually. There are some physicists working on that, and it's quite interesting. So maybe I should start investigating this as well.
So, sorry if this is a stupid question. Yeah. So when you sort of, as I think of it, you lift the singularity in the center of the black hole, which I'm very much a fan of, because I always thought singularities were really difficult to understand and really frustrating, because you think about what happens to matter, and you know, it can matter go and sort of become nothing when it was something. So, and if you have the classical Schwarzschild black hole solution, then you have a singularity at the edge, at the event horizon, and in the center. But then if the black hole is rotating, you get rid of the singularity at the event horizon, but you still have the singularity in the center. But in your theory, you actually also get rid of the singularity in the center. Is that sort of correct?
Yes.
Maybe
yes, it is correct.
Yeah.
Yes, it is correct. So at the event horizon of a Schwarzschild black hole, there is it's a coordinate singularity, which means that our time, which we use on Earth, or like or maybe more correctly, the time far away in the absence of any matter, the time of the flat Minkowski space-time. So that time cannot be analytically continued through the event horizon. It cannot be used as time coordinate in the interior of the black hole, and so it's called a coordinate singularity, but they are like coordinate transformations which can easily make the analytical continuation of that time. So we can create a time coordinate which behaves like our time, like in flat space time, but then it can go through and can be also used in the interior of a black hole or in the new universe. And that means that this is like a fake singularity at the event horizon. It's a coordinate singularity, which means it's not a real singularity. Real singularity is when curvature of space-time, and there are some invariants, there are some scalars. We can create like a square of the curvature tensor, which is a number, and the number is a scalar, which means if it has the same value in all frames of reference. So if this curvature square scalar is infinity, then it will be infinity for all frames of reference. So this infinity indicates a real singularity, and this is also related to the fact that the density of matter is infinite at the singularity, which means physics breaks down. This was frustrating me like 15 years ago when I was like starting investigating this, like in 2009 when I propose, and actually I discovered that I was not the first, because the idea that universe was created in a black hole was like, I think Igor Novikov was the first physicist in 1960, I think who came up with an article which he suggested that if black holes are charged, then there will be on the other side of the event horizon, there will be new space, and there'll be some continuation, and there may be something more beyond a singularity. Then some other physicists like realized that we don't need those black holes to be charged to make the new spaces, and
that's the whole black holes have no hair discussion.
yes, black holes have no here. It's a beautiful like property of a black hole. That black hole, like Schwarzschild black hole without rotation, is described only by two parameters, like the mass and. Actually, Schwarzschild black hole is described only by mass. It's only one parameter. But then, like, we can have also electric charge, and we also can have angular momentum. So there are only three numbers which describe a black hole, and at the same time we also have 3 numbers which describe an electron, which is, they are the same numbers. There is the spin, which is angular momentum, there is the electric charge, and there is the mass. So basically black holes are the simplest objects in the universe, in addition to elementary particles. They are all described by 3 numbers only.
So Igor Novikov actually was a professor at the Niels Bohr Institute for 15 years before he retired. So I actually had the honor of having him as a teacher when I was a student.
Awesome. This is
awesome.
This is very nice.
Okay, Nikodem, just a quick question. So if we are inside a black hole, and as Anja suggested earlier, someone in theory would be able to come and visit us. Or how do you view that? Could someone enter our universe from somewhere else? If we in theory could enter someone else's?
I guess
yes,
but it will take infinite long before it happens, right? Is that correct understood?
Actually, to reach a black hole, it takes infinite time for the observers far away from the black hole in the parent universe. Now, if someone entered a black hole which made our universe, and we are already in this new universe, then in principle we could see anything coming to our universe from the parent universe. However, like for example, like when we look at the moon, we see it not right now. We see it as it looked as it was 1 second ago, because light needs to travel 1 second from the moon to us. We see the sun. We see the sun as it was 8 minutes ago. We see galaxy of Andromeda as it was 2.5 million years ago. So if that white hole is like probably far away from us, like we don't know where it can be. It can be like somewhere far away. So if something like we would see that white hole not as it is now, we would see it as it was long time ago, which means if someone right now, it's actually difficult to even define what it means right now, because time is relative, but if someone was entering that black hole to come to our universe, we would see it after a very long time, because because during this process probably something would happen. So but then the light would have to travel from that white hole to us, so we could basically see that coming, this process of coming in. So it may happen, and depends where this white hole is. We could see it like after like billions of years. So
it could be close as well.
It would be close, and actually this is something which I was very
But could it be close, because we would see it as a white hole, right? So I'm thinking if it was close, we would probably have discovered it. Of course, we don't know what wavelength it's going to be a white hole.
Yes, yeah, it is. I'm still like learning like how white hole could be observationally detected, because for me as a theorist, like I just see them as the time reversal of Schwarzschild or Kerr. Actually, I never did in my calculations the Kerr metric. I want to actually do it to see how the rotation of the black hole would influence. And actually, there was this 3 or 4 weeks ago. I've seen in the media, and even I got cited like several times, that James Webb Space Telescope might have provided the first proof that we might be living in a rotating universe. And basically, Liam Shamir like wrote an article saying that according to his data analysis of some set of galaxies, it looks like that 2/3 of galaxies rotate counterclockwise and 1/3 galaxies rotate clockwise, as measured by us. And this can be either indication of some bias, because our Milky Way is also rotating, or maybe this may be indication of the fact that our universe is rotating as a whole. And in one of my earliest articles, I think it was my second article about the possibility that our universe was born in a black hole in 2010, in my summary, I wrote one little remark without investigating too much, but then the media captured that oh, Poplawski already said that. I mentioned one remark that if a black hole which formed our universe is rotating, is a Kerr black hole, then probably the universe on the other side will inherit this axis of rotation, and I don't know how it will manifest itself, but there might be some asymmetry in that universe. Maybe some fields will be different, some helicity of particles. So I just made a general remark. But then when I think about it, I want to actually investigate mathematically what happens, because I believe that if our universe was created by a black hole which was rotating, and all black holes, I think, rotate because everything in the universe is rotating. I think almost everything rotates. So a universe created by a rotating black hole should also have some kind of preferred axis of the universe, and maybe this asymmetry in rotations of galaxies may be indication. I don't know yet what direction this axis would be, but I believe that actually there are some arguments in mechanics which say that the universe should rotate about the axis which is the most likely axis of rotation of those galaxies. If there is some asymmetries, that galaxies tend to align with the universe rotation, just like all planets are rotating together in solar system, roughly. So if we have some confirmation that our universe has this axis of rotation, then it will quickly tell us where to look for this one and only one white hole, because this axis of rotation of our universe would be pointing to a white hole. To be well, now there are two ends of the axis. I mean, this axis has two directions, so this white hole can be either here or in the opposite direction. So one of those two choices.
The North or the South Pole.
Yes.
Very, very interesting, because as far as I'm aware, then all the black holes where people have managed to measure rotation seems to be rotating at basically the maximum speed, which we expect them to be rotating, which I find peculiar, probably natural. It's just that it was unexpected somehow, right? At least to me, it was unexpected that they were rotating.
I learned about it. I was it is very beautiful. I'm fascinated because I was reading at some articles about rotating black holes, because I was curious, how fast they rotate, and I discovered, wow, they rotate. There is the maximum allowed rotation for black holes to rotate. If they rotate more with bigger angular velocity, then space-time around them would have some strange behaviors, like the existence of the closed time-like curves, which those are the curves which allow traveling backwards in time. So basically, if we divide angular momentum of a black hole by its mass and by the speed of light, we will get this parameter which has a dimension of the size, and it's like a Kerr radius. And we also have the Schwarzschild radius, which is 2 times gravitational constant times mass of the black hole divided by square of the speed of light. So basically, to avoid any strange behaviors of the space-time, the Kerr radius, which is related to the rotation of the black hole, has its maximum value is 1/2 of Schwarzschild radius. And the articles I was reading were saying that the black holes they discovered rotating, they were rotating almost at that maximum angular momentum allowed. It was like 98%, 99%. I say it's fascinating. They want to rotate as much as they can, but always below. There's this censorship which does not allow them to rotate faster, which means they rotate quite quickly, which now tells me that the analysis I made about universes making new about black holes making new universes, I assumed Schwarzschild, and I said, oh, the Kerr black holes can introduce some small corrections, but now then my view is different. I say, well, they are not small corrections; those are huge things. Actually, this metric is not like Schwarzschild. It's like a critical Kerr metric. So I should see how to analyze the gravitational collapse in a rotating, like called extreme black hole, extreme Kerr black hole, and see how the universe on the other side will look like. But conceptually and like qualitatively, I would expect that there is a huge the axis of this preferred axis of that new universe. So, which means this asymmetry of rotations in galaxies, if it's 2/3, 1/3, that's a huge asymmetry. So this is an indication that this might be an indication that our universe was formed by a black hole which was like very quickly rotating, where those Kerr corrections were quite huge.
I mean, I love the way your whole face lights up when you talk about this stuff, Nikodem. I'm sure you're a great teacher as well, and it's been really fascinating hearing about your theories. I think this is all that we can manage right now, and we will do a few Danish breakdowns as well to help our listeners understand everything that you have been communicating. But it's been very exciting. And if you ever come to Copenhagen, let us know. We would love to meet you in real life.
Thank you. I would love to. I've never been in Denmark. I was only at the airport in Copenhagen several times on my way from Poland to United States. But I would love to visit Denmark, a beautiful country, and also
24 hours.
Niels Bohr.
Yeah, I'd be happy to show you the Niels Bohr Institute, and you can see Niels Bohr's office, which we still have, which is still standing like it was when he had it, and the famous Auditorium A, where all the famous physicists have been sitting, and we have all the pictures.
Oh, beautiful! So much nice history.
Yeah. I mean, Denmark and Poland have a lot of scientific history, and keep doing your awesome work, Nikodem. And thank you so much for your time.
Yeah, it's been super interesting. Thank you very much.
Thank you so much. Thank you so much.
Thank you for your time.
Awesome. I'm just going to stop recording.